Hello, everyone. Thank you, organizers, for inviting me here. Uh, I will talk about a Hopf algebra on non-crossing partitions. As Andu mentioned it in his mini course, is basically like the fourth lecture of the mini course of Andu. This is based on a joint work with Adrian, Kurush, Andu, and Leon, and the preprinting archive is down there. Part of this paper was already explained by Andu in his mini course, and I'm gonna talk in these 20-30 minutes on some other one or two sections of this paper. Okay, good. So what I want to discuss right now is first, like this Hopf algebra T on non-crossing partitions, such that the character group of the Hopf algebra is isomorphic to this group of semi-multiplicative functions that Andu has mentioned before. And then observe, so he already say why there is an inclusion between the multiplicative functions and the semi-multiplicative functions. And we are going to see this from the perspective of Hopf algebras by explaining a surjective homomorphism from this Hopf algebra that I'm going to build to the Hopf algebra that Andu mentioned earlier today. Okay. So, and at the end, I will mention some ongoing and future work that I'm doing on this. Okay, so let's start with the Hopf algebra T. Well, just recall a bit the motivation. So we have these semi-multiplicative functions. And some important thing to notice is that these functions only depend on partitions, on non-crossing partitions, right? So the functions are defined for intervals taking a smaller partition pi and a bigger partition sigma, when we have this semi-multiplicative property that allow us to write every function, every value of the function in terms of only intervals from pi to 1n. So I only need to know the values for pi's in the non-crossing partition. And I don't take the 1n partitions because I'm assuming that f1n 1n is always 1. Okay, which is very, very fair thing to assume. So then we have this convolution of two semi-multiplicative functions is defined in this way. Well, you take f star g, gf star f of two functions of pi 1n, then you write on the left the interval from pi to sigma, and then from sigma to 1n, and you sum over all sigmas that are bigger than pi in the order of partitions in refinement order, okay? Inverse refinement order. Now, the semi-multiplicative conditions allows me to take G, which is from pi to sigma, and break it into intervals that go up to 1n, or partitions with only one block. Okay, good. So now, the point that I want to make is, as Andu mentioned before, when you have a convolution of this type, you can always think of this as a dual of a Bialgebra or Hopf algebra. And in this case, we are going to do it over non-crossing partitions. Okay, good. So just an example to kind of understand better this convolution. So I have the convolution of GF, and I'm fixing a pi. Okay, so here I'm fixing this pi. And then I sum over all sigmas bigger than pi. So here's an example of one of those sigma. And then on the right-hand side, I have an f of sigma 1n. So the f is the value of the function on this sigma that is pictured here. And then the product of the g's is going to be over all blocks of sigma, and I restrict my partition P to the blocks of sigma, right? So in this case, I have pi restricted to the red block W is this figure. You can see how the picture here, if you just take the red parts, it becomes this. And the black one, this becomes okay. And okay, I'm sorry, I just put their crossing partitions. You can actually do that with crossing partitions, but yeah, in this case, I'm just working with non-crossing partitions. Sorry about that. Yeah, okay. Should have checked that. Anyway, just imagine that you modify these partitions and you make some non-crossing partition. It's actually a bad example because it's very, very crossing partition. Okay, sorry. Anyway, okay. Okay, so let's talk about the algebraic structure I want to put. So as I mentioned, the values of the functions only depend on the non-crossing partitions. So let me consider the set NC bigger than 2, which is all non-crossing partitions which have 2 or more blocks. And then the algebra I want to work with is the commutative algebra of polynomials over the complex numbers. And the indeterminates are going to be indexed by non-crossing partitions with 2 or more blocks. Okay. And you can also think of an indeterminate with partition with 1 block, but if you consider those, you want to identify all of them with the unit of the algebra. And the algebra, I call it T. Okay, so then, okay, yeah, so we have a universality property of this algebra. So whenever I have elements of some unital commutative algebra A, and I take elements indexed by non-crossing partitions. If I take all non-crossing partitions, then I need to restrict the values on the 1 block partition to be the unit of the algebra. And if I have such a sequence, then there is a unique unital algebra homomorphism that sends the algebra T to this algebra A, such that in the indeterminate x pi, I get the value of a pi. Okay, so that's some technicality that is very, I think, very intuitive, and we are going to use it just for some definitions. Okay, now something I would like a lot about the algebra, or is going to be the characters chi that are just unital algebra homomorphism from my algebra T to the complex numbers. Okay, and the point of taking this is now we can kind of recover the semi-multiplicative functions, because if you just take the values that the function from the indeterminate pi that goes to the semi-multiplicative functions with values with the same value in the interval pi to 1n, then you get like a bijection between the characters in this algebra and the semi-multiplicative functions that Andu mentioned before. Okay, so now what I want to do is to check the convolution. Okay, so for that I want to give a Bialgebra structure, and for that I need a counit. The counit is very simple. It's a function from the algebra T to the complex numbers, and I will set everything to 0, except of course for the unit goes to 1. Okay, because it's a unital algebra homomorphism. And here's where I just say the definition for x pi, but you can extend it for the whole algebra because of the anyway, yeah, it's just very easy to extend. And then the important thing, the combinatorial structure is summarized in this co-multiplication or coproduct. So this is a map from T to T tensor T, and again it's a unital algebra homomorphism. So since it's an algebra homomorphism, I just need to tell you the values on the generators x pi. And this is so if you remember the formula for the semi-multiplicative function, this is exactly doing this, right? So on the right-hand side, I take sigmas bigger than pi. And on the left-hand side, I break the pi into the blocks of sigma, and I take restrictions. Okay, so here pi w means the restriction of the partition pi to the block w of sigma. Okay, good. So now, in order to be a bialgebra or a coalgebra, it has to be co-associative. So the co-multiplication has to be co-associative, which is simply being the dual of the associative property of multiplication. So it's basically if you take the co-multiplication applied to t on the left or on the right, it's going to be the same. Then, okay, it's not so hard to check that this happens. And I can give a precise formula of the three things on the tensors. And well, it's also compatible with the counit. It's also not so hard to see. And then, so yeah, the compatibility with the counit is the fact that in this sum, you will always have x1n on the right-hand side because sigma 1n is always bigger than pi. And on the left-hand side, you can also get a unit there. And that's basically the explanation of why it's compatible with the counit. And okay, so now I have a bialgebra. Why is this useful? The idea is that I want to, something that could be very help to understand transitions formula is the antipode, okay? So the antipode on T gives a systematic way of computing the inverses of characters, okay? So characters form a group. I can take an inverse of a character. So in this group, my characters represent transitions formula. So for moment to cumulant, moment to free cumulant, moment to Boolean cumulant, moment to monotone cumulant, moment to T Boolean cumulant. And then if I want to invert those functions and then go from cumulants to moments, then I can just take the antipode. And only one thing, knowing the antipode will allow me to invert anything I want. Okay, good. And then, okay, so in this case, yeah, let's also, something we can do is to make an analogy to how the Hopf algebra sim that was mentioned earlier was used to study free random variables, right? Which is in the paper of Masnak and Nick. Good. Okay. So now, yeah, so this is a Hopf algebra. What does Hopf algebra? So a Hopf algebra is a bialgebra which also has an antipode. Okay, and the antipode has to satisfy some things. Now, explicitly giving an antipode of the bialgebra is not always easy, but if you know certain things, then you can be sure that there's going to be a Hopf algebra, that there's going to be an antipode. Okay, so now I'm going to mention some of these things. So you need to have a graded bialgebra, so you have to define a degree. In this case, very easy. So take x pi to be the size of the partition minus 1. And then you can extend that to monomials very easily, just respecting the algebra structure. Then this makes T a graded algebra and a graded bialgebra. Okay, so that only means that if you multiply things with certain degree, it goes to the degree, adding the degree, which is very fair, and exactly the same, but with the co-multiplication. Okay, and another thing is it is connected, and by this, the only thing I mean is the elements of degree 0 is just like the unit, and well, the complex copy, the copy of the complex number, which is given by the unit. This is also very easy to see because the partitions which have one block are the ones that give you the unit, and those are the ones that have degree 0. Okay, good. So now, by general considerations of Hopf algebras, if you have a graded connected bialgebra, then it is a Hopf algebra. Okay, and the idea is basically that, well, the reason behind this result is just that you can kind of do inductively define the antipode. Okay, so you define the antipode for the identity, then for the elements with degree 1, with degree 2, and recursively you can do that. That's the idea. Okay, good. And the antipode has to satisfy this property, which is if you take the coproduct, on one side you take the identity, and on the other side you take the antipode, and then multiply the result, which is this, then basically you get like a like the identity element. Okay, and it's the same if you multiply the other side. The way to look at this is kind of the dual of a inverse element. Okay, so in a group you have a product, you have a unit, and you have a inverses. In a Hopf algebra, the dual of these things are you have a co-unit, which is the dual of the unit, a co-product, which is the dual of the product, and the antipode is like the co-inverse map, sort of thing. Okay, good. So again, the most important fact that I want to mention here is that if you have the antipode, which is S, and then you have any character, you can obtain the inverse character by simply composing with the antipode. Okay, so yeah, that's a good systematic way of doing inversion. Okay, so now I will quickly go over the homomorphism from T to sim. Yes.
Did you actually define what F is?
S. Oh yeah, I have defined S. Yeah, I will mention some of it at the end. Yeah, S is the antipode. Sorry, so the S is the antipode, not? Yeah, I will mention a bit of that at the end. Yeah, yeah, that's a good question. Yeah, as I said, it's not always easy to just go and say, oh, this is the antipode. So that's why usually one in combinatorial Hopf algebras, one say, oh, it's graded, it's connected, then it should have an antipode. The antipode is unique, and then it takes some effort to explain what is the antipode. Okay, but I can say something about that at the end. Yeah, thank you for the question. Is there any other question? Yes.
Is it possible to give this a star structure?
The star structure. I'm not sure. Yeah, I don't know. That's a good question. I haven't thought about that. Not sure. Yeah, it's commutative. It's a commutative algebra polynomial. Yeah. Yeah, I'm not sure. I will think about that. There was another question.
Well, yeah, it's like finding, you're writing down the formula for the antipode. Is that like trying to find the Möbius function for a poset? You have to solve a bunch of equations, and maybe there's no nice formula, maybe there is.
Right,
But
exactly.
it always exists.
Yeah, yeah, that's kind of the idea. Yeah, if you're from the easiness algebra perspective, the antipode is kind of analogous to the Möbius function. And in sort of, yeah, I will mention this at the end, but it's kind of generalizing the Möbius functions that we have seen, like the Möbius function in the partitions, in the non-crossing partitions, in the intervals. You can kind of, this antipode kind of contains all of these formulas in a certain sense. So it's kind of general, but also more complicated, of course. Okay, good. So let me just briefly mention the surjetic homomorphism from T, the Hopf algebra that I've just created, constructed, to sim that Andu just mentioned before. So yeah, so this is a review of the Hopf algebra sim, but I don't think I have to go over it again. So this is what just mentioned 1 hour ago, or 30 minutes. So we have a Hopf algebra sim with a co-unit, a co-multiplication, a grading, and well, this is done in terms of elementary symmetric functions. But actually, what Andu pointed out earlier is that it's better to work with the parking function symmetric functions, at least in terms of the free probability. Well, the same, if we have these symmetric parking functions, then we have this degree. The co-unit is the same as before. Well, the co-unit is always kind of sending everything to zero except the unit. And the source of the combinatorial structures come from the co-multiplication, which, as I mentioned, is this kind of formula, which is kind of encoding the multiplication of free random variables. Good. Okay, and this is an example. Yeah, let's go directly to the result. is that we can send the Hopf algebra T to the Hopf algebra sim with a unital algebra homomorphism, which is defined as follows. So simply you take remember the Hopf algebra T generated by the x pi's, which have indexed by non-crossing partitions. So take a pi and then send it to the element associated to the Kreveras complement of pi. Okay, so Kreveras complement of pi is a partition, and sim was defined with integers, but of course you can take the products. Okay, so by y Kreveras of pi, I mean the product of the y's with the size of the blocks of Kreveras of pi. So then if I send this, if I define this map, this is a surjective homomorphism of Hopf algebra, of graded connected Bialgebras. Okay, so yeah, it's also a homomorphism of Hopf algebras. Okay, good. And yeah, as a corollary, well, as Andu mentioned, the character group of the symmetric functions is isomorphic to the multiplicative functions. Now, I didn't really tell exactly how this goes, but the character functions of my Hopf algebra T are in bijection with the semi-multiplicative functions. And then, well, if I take the dual of this Hopf algebra homomorphism, I will send is a way to embed the multiplicative functions into the group of semi-multiplicative functions. Okay. And yeah, well, this is the dual because it's simply composing the character that I have with the map that I have above. Okay. Good. Are there any questions so far? Okay, I guess I have like, do I have some time? 5 minutes? Good. So yeah, so let me discuss a bit about the antipode. Okay. So the antipode of T, well, there are in general for any antipode in any Hopf algebra, you can always have these Bogoliubov formulas, and these are kind of a recursive way of computing the antipode. Okay, so as I mentioned, like the idea is with this formula for the antipode has to satisfy this thing that when you take the coproduct, then the antipode on one side and the identity in the other side, and then multiply, you have to get like the unit in the algebra. So then using this is basically just writing down the formula, like really put it in terms of the coproduct. And once you do that and take some values on one side, then you express S of x pi in terms of partition with a smaller size, okay, or a smaller degree. So all of this is with a smaller degree, so you can recursively compute this, okay? And these formulas are useful. You can do the recursion on taking S on the right or taking S on the left, and both are the same. Some recursions are better for depending on what you want to do, okay? One is faster with kind of growing into the number of elements that the partition is partitioning, or growing in the size of blocks, the number of blocks of the partition. It depends. Good. Now, so also when there's like a kind of general way of defining of giving a formula for the antipode that is no longer recursive, that is like a specific way of telling you what is the antipode. And this can be done using chains. So a change of non-crossing partitions is simply taking several partitions, one smaller than the other, strictly smaller, in the reverse refinement order. And then this is the formula. So S of x pi is going to be a sum over chains going from pi to 1n. And then you have to put some sign there. and then you take products of products. So for each partition which is inside the other partition, I do this thing that appears in the coproduct, which is taking the restrictions of the smaller partition to the blocks of the bigger partition. And this has to be done for every pair of partitions that are consecutive on the chain. Okay, good. And this is very related to how Mobius function works, right? Good. Yeah, so one advantage or one thing that we found in this paper is that, well, this previous formula, for some pies, there's going to be cancellations here. So there are going to be monomials that appears twice in the formula, and they will appear twice or several times, and they will appear with different signs. So they will cancel. So somehow if someone wants to compute the antipode with this formula, they're going to write the formula and then will say, oh, but I have to cancel this and this and this, and it will be kind of not the best formula. So we found a formula which is a cancellation-free formula. Okay, so this means I can give you a upgraded formula where all the monomials here are not going to cancel. If they appear, if they appear two of them, they're going to appear with the same sign. So it's really like a formula that you will be able to use, well, more fast than the other one. Okay, so this is in terms of an efficient chain. It's not so easy to introduce what an efficient chain is, but I can just give you quickly an example. So in the case above, the chain in blue and the chain in red, both are chains of partitions. If you compute the monomials, so this means take the restrictions of the partition, this red one here, let me use the pointer, this restricted to this, and this restricted to this, and you take all the products. If you do the same in the blue one, you will get exactly the same monomial, okay? And then, well, in the previous formula, they will cancel because they will have different signs. In this case, you only consider the second one, which is efficient, and you get the sign that you need, okay? I can tell you more about this if any one of you is interested, but let me just go quickly to the last slide. So the ongoing and future work on this. This Hopf algebra or this semi-multiplicative function approach, the idea is that we want to have a systematic way to study any transition formula. So if you tell me, I want to know how to go from cumulants, Boolean cumulants to monotone cumulants, then I say, oh, I can do this. And I can do it using this group, basically group of characters or group of semi-multiplicative functions. So what we notice in the paper is that, as Andy mentioned also, there are important subgroups. For instance, the subgroup of cumulant to cumulant functions. And something that I've been working on and I have some results and I plan to have more is on other possible subgroups that really help to understand these formulas. The other thing are, there are like other Hopf algebra that can be related in this way. So I just show you a way to go from T to sim. There are other Hopf algebras, for instance, Hopf algebras on trees that can be also related to T. And that's kind of very interesting because you can there has appeared some relations to trees or to graphs. Like you take a partition and you reduce it to a tree, and then you study the tree, and then you get some results. And that also appears in transition between formulas. And there's a very concrete way of saying why is happening this. So that's interesting to relate this T Hopf algebra to Hopf algebras of graphs on particular trees. Yeah, in the same direction, there is this concept of T-free cumulants of Jekyll and Liu that they use T-free independence, kind of generalize Boolean, monotone, free independence, and other stuff. And they have T-free cumulants, and this transition between moment to T-free cumulants can be also captured with this Hopf algebra structure, with this group. So well, I'm working on understanding better this framework, and seeing if I can say something interesting. Yeah, something else could be, so far I told you is there a transition from one set of cumulants to moments or something like that. But there are formulas such as infinitesimal or conditional freeness that take two things, so two families, so cumulants and infinitesimal cumulants, or cumulants and free conditional cumulants, and then produce another thing, the moments or whatever. So they are taking two things and going to one. So this could be handled using, instead of a Hopf algebra of partitions, you can color the partitions. And then for one color, you put one thing, and for the other color, you put another thing. And that will be interesting to understand better. I'm working on that, but yeah, there's a lot of things that you can do on this. Thank you very much.